Welcome to this video in which we're going to discuss stability in the Z domain. Before you start watching this video, be sure that your knowledge with respect to stability in the S domain is on par and that you know the basic aspects about the root locus technique. Well, stability. What is the definition about stability? We can say that an LTI system, a linear time invariant system, is stable if every bounded input yields a bounded output. That means that an LTI system is unstable if any bounded input yields an unbounded output. In the S domain, it means that for that kind of a system, all poles should be located in the left half plane of the S domain. And we are going to see that a sampled LTI system, so defined in the S domain, is stable if all poles are located within the unity circle in that Z plane. And that is the topic of this video. So let's start off with the relationship when we start in the S domain and transform to the Z domain. This was the definition for the S operator, the Laplace operator S. And S was equal to lambda plus J times omega. And this definition comes from the exponential harmonic signal, in which lambda is the damping factor and the omega is the damped angular frequency in radians per second. And when we went to the Z domain, we defined Z as e to the power s times t, in which s is that Laplace operator here, and the t, the capital T, is the sampling time. So we define that in this way, so we can also say that z to the power minus 1 equals e to the power minus s times t, which is a delay. So z to the power minus 1 equals a delay. So these two expressions are really crucial for our analysis. So when we substitute s in this expression, then we get z equals e to the power lambda plus j times omega, this expression, times t. And we can work that out, and we get e to the power lambda times t times e to the power j times omega times t. When you look to this definition, this is the definition of a complex number, in which this is the amplitude of the complex number, the absolute value of z, and the phase of my complex number is everything within this power except the j. So the argument, or the phase, equals omega times t. So we have an Euler notation of a complex number with e to the power lambda times t as the amplitude and omega times t as the argument, or the phase. And remember, in the S domain, we define as the border between instability and stability as the imaginary axis, so the axis where the lambda is 0. So everything in the left half plane was stable, and when one pole or more poles are in the right half plane, we have an unstable system. So we have to look to that border in the S domain where lambda is 0. When we fill in that lambda is 0 in this expression, we see that that amplitude equals 1, because e to the power 0 times t equals 1. So the transformation from the border of our stability in the S domain, so the imaginary axis, is transformed to the Z domain in a way that my amplitude becomes 1 and my phase is still the same. It's omega times t. So I'm looking to a figure in which the amplitude is always 1 and the argument, or the phase, keeps on increasing when omega increases. And that is a unity circle, a circle with a radius of 1, and of course the phase can keep on going. So this is the unity circle. It stands for the border, like the imaginary axis in the S domain, but then in that case transferred to the Z domain. So when one or more poles are in the right side of my S domain, we are unstable. which means that in a sample situation in the Z domain, when one or more poles are outside the unity circle, we have an unstable system. So we have a requirements to the poles of our system. They have to be, all of them have to be in the unity circle to have a stable system. That is our requirement according to this definition, or these two definitions, I should say. Well, let's have a look to an example. And in this example, I have a system, H2, and that system is preceded by a zero order halt. And that zero order halt is defined as 1 minus e to the power minus st over s. That's the definition of our zero order halt. And it's controlled by a controller H1, and you can see we are going to use a proportional controller with only a k in it. So when we have to make the transformation to the Z domain, we have to do the transformation of this complete system, and let's call that H3. And let's define H2 as a simple system, a first order system. But for transformation to the Z domain, we have to transform everything between samplers. This is a sampler and that is a sampler. So we have to take the Z transform of this complete expression, which is the cascade system or the series connection of the zero order halt times H2. So we have to transform that to the Z domain, and when you work that out, you get this expression. And I will explain how we come to this expression. So again, I have a controller, proportional controller K, and I have an expression in the Z domain, which is a Z transform of the cascade system of my zero order halt and my process H2, which is in this case a first order system. So let's have a quick look how that transformation of this complete cascade system to the Z domain, how that worked. This was my H3, which is 1 minus e to the power minus st over s, and this is h2 1 over s plus 1. So this is a combined function h3, and we are going to transform that to the Z domain, so we are taking the Z transform of this complete system. And what we can do, obviously, we may transfer this as 1 minus z to the power minus 1, because that is the definition of my z. E to the power minus st, a delay, is z to the power minus 1 in the Z domain. So we have to multiply that by the Z transform. This is the Z transform of my the rest of my system, 1 over s times s plus 1. So we can split that out using partial fraction decomposition, and then this becomes 1 over s minus 1 over s plus 1. So again, we have this as a Z transform of this part of my equation, and now we have to take the Z transform of 1 over s minus the Z transform over 1 over s plus 1. The Z transform of 1 over s is Z divided by z minus 1, and the Z transform of 1 over s plus 1 is equal to z divided by z minus e to the power minus t. When we work that out, we can, the best thing to do is we can get rid of that z to the power minus 1, so we can write that out as z minus 1 over z. You can see it, z over z is that 1 over here, and 1 over z is equal to z to the power minus 1. And now we can multiply this part by that part, and this part by that part. And then we get this by that yields 1, and this part by that part multiplication is z to the power minus 1 divided by z minus e to the power minus t. The last thing we can do is to make it more easy and to be able to look to the poles and the zeros is to get that 1 in the same expression with the denominator, which is equal to this denominator, z minus e to the power minus t, and then we get z minus e to the power minus t over z minus e to the power minus t. So we can subtract the numerators in that case, and we get h3 in the Z domain equals 1 minus e to the power minus t divided by z minus e to the power minus t. So this is my expression of that complete system over here, consisting of the z transform of the cascade system of the zero order halt and my system, my first order system, H2. Well, now let's look to the stability. This was my proportional part, and this is H3. So first of all, let's have a look to the open loop. How many zeros do we see in this expression? Well, there's no expression with a z in the numerator, so we don't have any zeros. Do we have any poles? Yes, we have, because we have a z in the denominator, so we have one pole, and that pole is located at the location e to the power minus t, and you can get that, of course, by setting the denominator to 0. Well, when we have to look to the stability of my closed loop system, the best thing we can do is get an expression of my closed loop system C over R in Z domain. So then we can say it's a combination of all the blocks in the Z domain in the forward path. So H1 in the Z domain times H3 in the Z domain, which is expressed over here, divided by 1 plus H1 in the Z domain times H3 in the Z domain, which is expressed over here. We can fill it in. H1 is K, H3 is this expression. When you work that out, you get this expression as the closed loop. And of course, when we want to look to the stability of a system, we have to look to the poles. So we have to set that denominator to 0, and then we get a location of the pole. And you can see that that K is still a part of that expression, which is the proportional gain. And now we are going to use the rules of the root locus equation in order to see how my pole, because we have only one pole, how it moves as a function of an increasing K. So when K starts to increase from 0 to infinity. So in that case, we can see what the pole locations will be, and in what case this system is stable, and in what case this system is unstable. So when we have this as an expression, and we want to look to the stability of the system, we are going to look to the location of that pole, and we call that the root locus equation. So the root locus equation is nothing more or nothing less than the equation for the poles of my closed loop system. But what we mostly want to do is write it down in another way, an expression that we get this kind of expression: 1 minus e to the power minus t divided by z minus e to the power minus t equals minus 1 over k. Why do we want this expression? When we have this, you can say in words that all the system blocks in the loop, so all the system blocks in the loop, well, this is a system block, this is a system block, and here is only a system block of 1. All of these system blocks, except for the controller, so we leave that out, is equal to minus 1 over k. And when we get this expression, which is a normal expression for the root locus equation, we can look to the root locus rules and draw the root locus and see how this pole is going to move, and we're going to look how of when instability starts. So we write it out in this way, and that is what we did over here. But you can always see it directly by saying all the system blocks in my open loop, except for my proportional gain over here, have to be equal to minus 1 over k, and then use the rules of my root locus. So what are the basic rules of the root locus? Well, there are two rules which are always important. The first rule is that every branch of my root locus starts in a pole, and every branch ends in a 0. But when there are less zeros than poles, then that branch could end in infinity. That's rule number 1. And the second important rule is that you have to define which part on the real axis belong to the root locus. And to check that, you work from right to left on the real axis, and you count the numbers of zeros and poles together. And when that number is odd, then the part on the root locus left of that pole or zero which you are going to pass. So when that is odd, then that part of the real axis belongs to the root locus, and when the total number of poles and zeros is even, then that part of the of the real axis does not belong to the root locus. Well, these two rules are important, and we are going to work that out in this example. So this was my root locus equation, and we wrote that in the normal way. So from this expression, we can see we have no zero and we have one pole, and that pole is on the location z equals e to the power minus t. So this is my location of the pole at the position e to the power minus t. And you can see that the sample time t is still part of that location. So the pole may be at a slightly different location depending on the value of the t. So we know the root locus starts off in the pole, and we don't have any zeros, so the root locus has to end in infinity. And now we can check which part of the real axis belongs to the root locus by going from right to left on the real axis, and then we count the number of poles and zeros we pass. So in this case we pass one pole, so the total number of poles and zeros we have passed in this situation is 1. And 1 is an odd number, so this part of the real axis belongs to the root locus. And there is no other pole or zero coming, so this is my root locus. What we have drawn in this figure is also that unity circle. We have said that all the poles have to be within the unity circle in order to get a stable system. So when my pole starts to move, when I increase my k, so my proportional part, we have to make sure that this pole never leaves the unity circle, because at that value of my proportional gain, my system, my closed loop system will become unstable. And that instability point happens over here. So when the pole is in -1, I'm just at the border of my unity circle, my system starts to oscillate and will not be stable anymore. So this is the boundary in this case for stability. So in that case, we can also calculate the value of the oscillation value of k, of my proportional part, by substituting -1 in the z over here. So we substitute -1 in this expression, and then we get the value of my k in which this system starts to oscillate, which is in this situation 1 plus e to the power minus t divided by 1 minus e to the power minus t. So you also see it still depends on the value of my sample time. So when we choose a sample time of 1 second, the oscillation value of k is 2.16. So for all values in this closed loop, in this example, for all values of k which are smaller than 2.16, my system is stable, and when I increase this value, my closed loop system will become unstable. So this is an easy example with a first order system for H2, but when we have more complex systems, of course, we get a more complex root locus, and we are not going to do that by hand, but we are going to use MATLAB. For example, when we have a second order system, so when we have this kind of a system for H2, and we are going to use, or we're going to define this in the Z domain and try to calculate the root locus, it will be a really difficult part for a sketch by hand, so we're going to do that by MATLAB. For instance, when we draw that, you can see that we get a root locus which looks like this. When you transform this complete system GOH, so the zero order hole times H2, and get the Z transform of that system, it yields two poles, one in 0.25 and one in 0.5, and we get 1, 0 in -0.5. And the root locus looks like this. We have two poles, so we have two branches leaving. One has to end up in that 0, but we have only 1, 0, so the other branch has to end in infinity. And what you see is when the k increases, these two poles starts to move somewhere in between, and then they split off with a circle movement, and they end up over here, and then this pole goes to the left to infinity, and the other pole goes to the zero over here. And of course, these two intersection points, they are crucial because at this point and at that point, these 2 points, my poles start to leave the unity circle. So for values of k which are larger than the k belonging to the pole location over here, which seems to be 14, then my system becomes unstable. Well, you can calculate it by hand, but it takes a sunny afternoon to calculate that by hand, so we are going to use MATLAB. And I'm going to show you a small demo in which you can see that it really is starting for k is 14. So I'm going to MATLAB, and I had a small script over here in which I defined h2, and I defined the sampling time of ln2. And remember, in MATLAB you have to define the ln of 2 as the log of 2. I'm going to use the MATLAB command c2d to z-transform my system plus my zero order hold to the Z domain. And c2d, continuous to discrete, is a very useful function in MATLAB to do that transform by giving the first parameter or filling in the first parameter, the system I'm going to Z-transform, yielding or using the ZOH, zero order hold transformation the transformation form, so to say. So I'm going to use Z zero order hold transformation, and at parameter number 2 I have to define the sampling time, which is defined over here. So this is my H2 discrete, is my H3 in the example I showed you. And now I'm going to close the feedback loop, and there is another useful MATLAB command which can do that very easily, which is a feedback command. So by using the feedback command, I can define a feedback system in MATLAB with a unity feedback over here. So there's no expression, no other block in the feedback path. And then I'm going to use the command root locus to show the root locus by generating a figure with that root locus. So let's do that. And there we go. And here we have my root locus, and you can see it over here. And here we see at the border, we see also what we saw from a hand calculation over here. We see 2 poles, one pole at 0.25 and one over here at 0.5. And when you have these poles, you can see that one branch starts is going that way, one pole is moving in that way, and one pole is moving in that way. So you can move this cursor over here, and then you can see there we go, this went that way. That at this point we are at the unit circle, which is that dashed circle over here, and we can see that, well, it's a gain of 14.3 it says, but I didn't put it exactly on the unity circle. So we can see that almost at 14 we have, here we are at 14, we are exactly on the unity circle. So at 14 we have a gain at which my system becomes unstable. So it's very easy to use MATLAB for complex systems to see at what values of k my system will become unstable. So summarize, it's very important to look to stability also in the Z domain, and except for looking to the poles in the left half plane in the S domain, you have to look to the position of the poles in the Z domain, and all poles of your system, whether it's an open loop or a closed loop system, have to be in the unity circle. That's it. Thank you for watching. I'll see you next time.